Hi, welcome to a lecture on the directivity of a uniform linear array. The array we're going to consider in this lecture consists of current moments aligned along the y-axis as shown in this figure. Each current moment is aligned in the z-hat direction, and they're separated by a distance d. And there are n such current moments. So the description of this array is given in terms of the volumetric current density of each one of the n elements, as indicated in this expression, z hat times the current moment I sub n delta L times the spatial sampling function. The sampling function has an argument of r minus p sub n, where p sub n is n times d times a y hat, simply reflecting the geometry of the array as indicated on the left. And then n, of course, goes from 0 to n minus 1 for n elements. We're going to make an additional constraint here that I sub n equals I sub naught. In other words, all the excitations are equal to that on element n equals 0, which we will refer to as the reference element. This is referred to as uniform excitation, and this will result in a beam in the xz plane. Because the elements are aligned along the y-axis, we expect maximum directivity under uniform excitation to be perpendicular to the y-axis. However, note that pattern multiplication plays a role here. Pattern multiplication simply means that the beam that you get is a product of the element pattern and the array factor. So, whereas the array factor results in a non-beam-like thing, which is simply maximum directivity in every direction perpendicular to the y-axis, the element pattern, which is this dumbbell shape that I'm drawing now, has a null in the z-axis direction. So the overall pattern of the beam will be in the plus and minus x hat direction. Let me draw a picture of that. Okay, here's the picture. Here are the elements. And then the beam has two lobes, one in the plus x hat direction, one in the minus x hat direction. The array factor in general is given by this expression, but we invoke uniform excitation. And we also note that r hat, that is the unit vector that points towards the field point, is given by this expression, which you can derive on your own or which you can get from the early chapters of any electromagnetics textbook. We take this dot product here. We note that p sub n has only a y hat component, so the only component that survives the dot product is sine theta sine phi. And so this is what we see in the exponent after taking the dot product. We factored out the uniform excitation, I sub naught. And then for convenience, we're going to make a definition. Here is the definition. We're going to define xi to be beta times d times sine phi times sine theta. And that lets us rewrite the array factor as I naught sum over n equals 0 to n minus 1 e to the j n xi. Just a convenient way to shorten the expression. Note that the maximum value of the array factor is n times I naught. That is, here's I naught, and then this whole thing has a maximum value of n, right? Because the magnitude of e to the plus j anything is 1, and if they all align in phase, then this expression will add up to n. So the maximum value of the array factor magnitude is n times I naught. Now, to simplify the analysis, it's going to be convenient to express the array factor as a trig function. Right now, it appears as a sum of complex exponentials. So here's what we're going to do. We're going to take that sum of complex exponentials and write it out. So for n equals 0, we get 1. For n equals 1, we get e to the j xi. For n equals 2, we get e to the j 2 xi, and so on, up to the final term. Now we're going to look at that expression, and we're simply going to multiply it by e to the j xi. And what that means is that 1 will become e to the j xi, e to the j xi will become e to the j 2 xi, and so on up to e to the j capital N xi. So now we have two expressions, and we're simply going to subtract them. So when we subtract them, on the left, we get this expression, and on the right, we get simply 1 minus e to the j capital N xi. So by doing this, we've collapsed a sum of n terms into two terms. Next, we rewrite this as the sum from 0 to n minus 1 e to the j n xi becomes simply this fraction. 1 minus e to the j capital N xi over 1 minus e to the j xi. Next, we multiply by this fraction, which looks a little bit convoluted, but it serves a purpose. So in the numerator, we have minus 1 over 2j, e to the minus jn over 2 xi. In the denominator, we have a similar looking thing, except without the n over 2. We multiply through, substituting the expression that we have just derived, and we obtain this expression, this new fraction. And perhaps you see that this is a well-known trig identity. This is a way of writing the sign of something. So using the trig identity, we note that this is simply sine capital N xi over 2, and the denominator, we end up with sine xi over 2. So we have transformed the sum of complex exponentials into the ratio of sine functions. So now we put all this back together, and we find that the array factor can be given by this constant a sub naught, which I defined over here to account for this whole complicated looking thing, times I naught, times the ratio of these sine functions. Now just a side note here, that ratio of sine functions is very similar to sinc. The maximum magnitude of that thing is capital N, and that occurs when phi equals 0, which is xi equals 0. Also, it occurs when theta equals 0 or pi, but that's not really relevant because the pattern null that we get will clobber that, right? That array function times the element pattern is the total pattern, and the element pattern has a null at theta equals 0 and pi. We'd like to write down now the normalized pattern function. This plays a role in the strategy that we will use to determine the directivity. The expression that we derived in a previous lecture looks like this. The normalized pattern function is a function in general of theta and phi in primed coordinates, and we obtained an expression that looked like this, which was the array factor times sine theta. Remember that sine theta is talking about the element pattern, and the array factor is talking about the array geometry and excitations, divided by the same thing except evaluate in whatever direction it's maximum, such that this pattern function has a maximum magnitude of 1. Here the problem's relatively simple because the primed coordinates we can make equal to the unprimed coordinates because all the elements are oriented in the z-hat direction, so both theta and phi can be expressed simply as unprimed coordinates. And so the normalized pattern function is simply array factor times sine theta, that is the element pattern, divided by the value of the numerator in whatever direction it is maximum. So we apply that here, and we get, just making the substitutions, a naught, I naught, ratio of those sine functions times sine theta, and then the denominator, a naught, I naught, times n, because n is the maximum value of that function, and the direction in which that is achieved is theta equals pi over 2, so it's sine pi over 2 over here. So now cleaning up, we have 1 over n, ratio of those sine functions times the element pattern. And we can interpret these factors, right? This is the element pattern. This has to do with the array geometry. It's a version of the array factor. And this is a normalization. So that is a normalized pattern function. The next step in computing the directivity, according to the default recipe that we've established in a previous lecture, is to compute the beam solid angle. That's omega sub a. this is the definition that we came up with. It's integration over sphere of the normalized pattern function squared, or what we would call the normalized power pattern. And then this is just the differential element of solid angle. So making the substitution, we get 1 over n squared. In the integral, we get magnitude of that ratio of sine function squared. We get a sine cubed theta, d theta, d phi. Now, there are many ways to solve this integral, including ways that will give you a closed form expression. It's relatively complicated, and to be honest, is really not necessary here. In other problems, we'll end up with similar, somewhat ugly integrals that will not yield closed form solutions, so I don't really feel it's necessary to write down the closed form solution for this one integral where we can get a closed form solution. Generally, numerical integration will be suitable in the vast majority of problems where this comes up. Now, directivity is simply given by the ratio of 4 pi steradians divided by the beam solid angle. So there's a numerical integration to do here to get omega sub a, the beam solid angle, and then you just divide that into 4 pi. That gives you the directivity. So before we charge ahead, let's just make sure that this works for n equals 1. That is 1 current moment. And the reason is because we already know the solution for that. In the case of n equals 1 current moment, the beam solid angle is just 1 over n is 1, so 1 over 1 squared. Integral, this thing, evaluated for n equals 1, is just 1, so that's simple. And then we're left with sine cubed theta, d phi. That factors into 2 integrals. This integral, the integral of sine cubed theta from 0 to pi, is well known. It's probably appeared in previous lectures. It's 4/3. The other integral is pretty easily seen to be 2 pi. So we get that the directivity, being 4 pi over beam solid angle, is 4 pi over 8 pi over 3, which is 3/2. And this is indeed the directivity of a single current moment. 3/2 are 1.5 or 1.76 dBi, all the same. In any event, that check works. So at least this works for n equals 1. So, before we compute the directivity, I would like to show some power patterns, because having the power patterns be right is going to give us confidence that the directivities that we compute are reasonable. So first, the simplest possible case that we can imagine, again, is n equals 1. That's just 1 current moment. And I'm showing power patterns, that is the magnitude of the normalized pattern function squared, in 2 planes. And I refer to these as the E plane and the H plane. The E plane is phi equals 0 degrees and varying theta. So if we go back up to the original picture, the E plane is, for example, the plane containing the Z and X axes. The H plane, which we'll refer to, is the plane containing the Y and X axes. So they're 2 perpendicular planes meant to give a relatively easy to understand overall picture of what the pattern looks like. So the E plane here, the pattern is 0, very, very small, at 0 and 180 degrees. That's, of course, because of the element pattern having a null in those directions. And as we anticipated earlier, the maximum directivity is going to be at 90 degrees or pi over 2 radians. None of that is surprising. Effectively, this is just the element pattern. The H-plane is simply 0 dB, or a value of 1, for the whole range of angular values here. Again, not surprising. This is just showing that the n equals 1 array is the same as a single element, which is what we expect. If we go to n equals 2, the E-plane is going to be the same. Nothing is going to change in the E-plane. Doesn't matter how many elements we have, there's no reason to expect that the normalized power pattern will change. That's not saying anything about the directivity. We're just plotting power patterns at the moment. If I choose the spacing between these elements to be wavelength by 2, as I've indicated here, then the H-plane will now look like this. So now the H-plane indicates some directivity. The maximum directivity is broadside to the array. It's right about here. And of course it falls off as you go towards end fire. If we increase the number of elements to n equals 3 and keep the spacing the same, you get what you might anticipate. That is a narrower beam. The beam becomes narrower because the array is bigger. And this is the precise form you get for n equals 3 wavelength by 2 spacing. You may note, however, that there is this thing coming back up. Well, that's just a side lobe. And remember, this is only half of the pattern because we're going from minus 90 degrees to plus 90 degrees. So if we draw a polar plot of the whole pattern, it would look something like this. We're just showing this part of the pattern. Now we go to 10 elements. We'll keep the spacing the same at half a wavelength. And this is the new result. Because the array is somewhat larger now, we get a narrower beam. And here's our narrower beam being indicated here. And now we have lots of side lobes, and the side lobes are rolling off with distance from the main lobe. Okay, all that seems to be making sense, so let's go ahead and plot directivity versus element spacing. The plots I just showed you were for element spacing of 1/2 wavelength. In other words, the plots I just showed you fall here on this plot, where this plot is showing directivity in linear units, not in dBi, as a function of element spacing and wavelengths. So the 3 cases I just showed you are here for n equals 1, here for n equals 3, and here for n equals 10. Now what you see is that regardless of the number of elements, the directivity increases with increasing spacing at least through 1/2 wavelength. But then, and this is most clearly seen for n equals 10, and that is large number of elements, the directivity continues to increase to some threshold amount and then collapses. And we see that is the same trend regardless of the number of elements in the array. In other words, the peak directivity is achieved somewhere in here, somewhere between 0.5 and 1 wavelength. Note well, folks, it's not achieved at 1/2 wavelength. It's usually achieved somewhere greater than 1/2 wavelength, but less than 1 wavelength. This is a common misunderstanding. As you continue to increase the spacing, then eventually you get to a point where there's a crash. Now, what's going on when the directivity becomes suddenly much smaller? We'll address that in just a moment using the patterns. But let me summarize a few ideas here. First, I've obtained these plots by numerical integration. That is, I used numerical integration to get omega sub A, to get beam solid angle. Again, you can come up with a closed form expression, but I think numerical integration gives you good practice in doing more complicated problems. The headline in this plot is that the element spacing has a big effect on the directivity. Directivity depends on element spacing, not just on the number of elements. So both play a role. Okay, so what's happening with this decrease in directivity with increasing element spacing? To address this, I'm going to show you H-plane patterns for n equals 10. All 3 of these are for n equals 10, but for 3 different spacings. The spacings will be 0.9 wavelengths, which is close to the thing that gave us the maximum directivity, spacing equal to a wavelength, and then spacing equal to 1.1 wavelengths. What you should note is that as the spacing increases, these side lobes are getting bigger. At half a wavelength and 10 elements, these side lobes were pretty small. But now they're creeping up as the spacing increases. We get to a wavelength, and suddenly we get full strength side lobes which are as big as the main lobe. So at this threshold value of 1 wavelength, the side lobes are as big as the main lobe. Antenna folks call these side lobes grating lobes. As the spacing increases beyond 1 wavelength, here 1.1 wavelengths, not only do you get full strength side lobes, but also they start moving in. They start moving towards the main lobe. So things are getting even worse. However, to answer the question, what's happening to cause the crash in directivity with increasing element spacing, it's simply that these additional lobes are showing up so that the main lobe is no longer primarily responsible or solely responsible for the directivity. Now all these side lobes are contributing to directivity as well and reducing it. Another way of thinking about what's going on here is in terms of aliasing. As we reduce the element spacing, the way we can alternatively think about this is that the aperture, which is being filled out by the elements, is undersampled. Really what's happening here is just the Nyquist sampling theorem, but now applied in the spatial domain to arrays instead of to sampling intervals in a time domain waveform. And evidently what happens is that as you increase the element spacing, which is analogous to reducing sampling frequency, you hit a threshold where the aliases become apparent. By the way, this connection with time domain sampling theory extends in other directions. For example, here's another interesting and useful connection. Note that in all three of these cases, n equals 10, 0.9 wavelengths, n equals 10, 1 wavelength, n equals 10, 1.1 wavelength, in each case, the closest in side lobes were always 13 dB down. That was true regardless of the spacing. Now you may recall from an earlier course or some course that you've taken in signal processing that the side lobes of a rectangular window are minus 13 dB. And that's not a coincidence. It's not a coincidence that the peak of the side lobes closest to the main lobe are minus 13 dB. This is simply the Fourier transform of a rectangular window. In other words, the elements in this array are sampling an aperture. That aperture is being uniformly illuminated because we forced all the excitations to be equal. It's essentially a rectangular window, but in the space domain, not in the time domain. And as a result, we see side lobes, which are 13 dB down. By the way, this suggests that we could manipulate beam width and side lobe levels by choosing the appropriate non-uniform values of I sub n. And that's totally true. In other words, we could choose to make the magnitudes non-uniform, maybe triangular over the distribution, and thereby end up reducing these side lobes and broadening the main lobe. That's totally possible and a topic for another lecture. But since I bring it up, I would like to conclude this lecture with the specific analogy: time domain sampling and spatial sampling. And by time domain sampling, I mean traditional Fourier theory, and by spatial sampling, I mean array theory. In time domain sampling theory, we have time and frequency, and they're related by a Fourier transform. You take a time domain waveform, take the Fourier transform, you end up with a spectrum. In spatial sampling, position works like time, where position is, in this case, element position along y. And spatial frequency, that is wave number, that is beta times sine phi sine theta, works like frequency. And is totally true if you take the excitations along position and take the Fourier transform, you end up with these plots. And you can go backwards. If you want a particular pattern, say you want this pattern, you can figure out what excitations will yield that by taking an inverse Fourier transform. So this connection is very, very useful. That concludes this lecture on directivity of a uniform linear array.